Hello, my name is Bonnie Curtis, and I'm a noise analyst with the Department of the Navy. Today I would like to talk to you about the science of noise and how the Navy assesses noise. Sound, it's all around us. Sound, simply defined, is a series of complex vibrations that originate from a source and travel through a medium, such as air. These vibrations are known as compression waves. Just like a pebble dropped into a pond creates ripples, the compression waves formed of air molecules pressed together radiate out, decreasing or attenuating with distance. If these vibrations reach our eardrum at a certain rate and intensity, then we perceive it as sound. Whether that sound is interpreted as pleasant, such as music, or unpleasant, like a jackhammer, depends largely on the listener's current activity, past experience, and attitude toward the sound source. Sound becomes noise when it interferes with our normal activities, such as sleep or conversation. In environmental noise analysis, we measure sound and relate sound levels to community annoyance and activity interference. The measurement and human perception of sound involves three basic physical characteristics: intensity, frequency, and duration. Intensity is a measure of the acoustic energy of the sound vibrations and expressed in terms of sound pressure. The greater the sound pressure, the more sound energy, and the louder the perception of that sound. Frequency is the number of times per second the air vibrates or oscillates, expressed in cycles per second or hertz, and determines how the pitch of sound is perceived. And finally, duration is the length of time the sound can be detected. The loudest sounds that can be detected comfortably by the human ear have intensities that are 1 trillion times higher than those of sounds that can barely be detected. Now, because of this vast range, using a linear scale to represent sound intensity is unwieldy. Instead, noise experts use the decibel, expressed as dB. It is a logarithmic ratio to represent the sound pressure level that is detectable by a human and closely matches the human perception of sound. The human auditory system is not equally sensitive to all frequencies. While the frequency range of the human ear goes from 20 to 20,000 cycles or hertz per second, we hear best in the range of 1,000 to 4,000 hertz. For environmental analysis, we need a way to measure the same way the ear hears it. The A-weighted sound level achieves this goal. Sound levels are measured using A-weighting, called A-weighted sound levels, and often denoted as dBA. A-weighting is a frequency-dependent adjustment of sound level used to approximate the natural range and sensitivity of the human auditory system. The U.S. Environmental Protection Agency, Federal Aviation Administration, and Department of Defense have all adopted a weighted sound level as the federal standard for environmental analysis. The term noise metric refers to the unit that quantitatively measures the effect of noise on the environment. Noise metrics quantify sounds so they can be compared with each other and their effects in a standardized way. The DoD and the Federal Aviation Administration use three common noise metrics to quantify sound. First, a measure of the highest A-weighted sound level occurring during an individual aircraft overflight. This is referred to the maximum sound level, or LMAX. Second, a combination of the maximum level of that single event with its duration. This is referred to the sound exposure level, or SEL. And third, a description of the noise environment based on the cumulative flight and engine maintenance activity. This is known as the day-night average sound level, or DNL. And now a little bit more on DNL.
The DoD and other federal agencies use the day-night average sound level metric, or DNL, to describe long-term noise exposure from aircraft operations. DNL does not represent the noise from a single aircraft operation, but rather represents the total accumulation of aircraft noise from all aircraft operations over a 24-hour period. It takes into account the maximum noise levels, the duration of the events, and the number of events that occur over a 24-hour period, as well as human sensitivity to noise. To illustrate this concept, The area shown in orange represents the noise associated with aircraft operations that occur over a 24-hour period. DNL is adjusted to account for the increased human sensitivity to noise at night. Each nighttime operation occurring between the hours of 10 p.m. and 7 a.m. is weighted the same as 10 daytime operations. Now, to account for nighttime operations, the area shown in blue represents the noise level adjustment for aircraft operations that occur between 10 o'clock p.m. and 7 o'clock a.m. This acoustical nighttime adjustment accounts for the added intrusiveness of noise that occurs during normal sleeping hours, both because of the increased sensitivity to noise during this time and because background sound levels are typically lower. Then, the noise exposure from the daytime operations, the orange area, and the nighttime operations, including the influence of the acoustical nighttime adjustment, the blue area, are added together and evenly distributed over the entire 24-hour period. This noise level, the green line, is the DNL.
Noise modeling is the accepted method by both the Department of Defense and the Federal Aviation Administration for noise impact analysis in areas adjacent to military airfields and civilian airports. It is conducted according to established DoD guidelines and best practices. It involves extensive data collection, validation, and analysis, and is subject to a rigorous technical and quality assurance process. Science supports noise modeling as the most accurate method to predict community noise exposure levels around airfields. It provides the prediction of noise levels at a large number of locations for a given set of conditions, including both current and proposed conditions. It allows the DoD to predict sound levels for aircraft that may be stationed at an airfield in the future and changes to flight operations that do not currently exist. Noise modeling also accounts for multiple variations that occur throughout the year, such as weather conditions, runway usage, and operational tempo. Noise models are based on scientific principles and measured noise data. Noise modeling provides accurate prediction of noise levels through careful collection of data on noise source operations, use of databases of measured aircraft sound levels, and validated sound propagation theory. Noise map is the DoD noise model used to describe the noise environment near military airfields. It is a suite of computer modeling programs that include a user input interface, a database of measured sound, power, distance data for military and civil aircraft, core propagation programs that calculate the resultant noise over a defined grid of points or a specific point, and finally, an output program. The Noise Map Output Program produces day-night average sound level noise contours used in noise analysis for the National Environmental Policy Act and the Air Installations Compatible Use Zones, or AICUZ program. I would now like to discuss noise data and noise levels from the EA-6B Prowler aircraft that has long operated from Naval Air Station Whidbey Island and the EA-18G Growler aircraft that has replaced the Prowler. The Growler noise profile is based on extensive noise measurements taken from the actual FA-18 Super Hornets, both in flight and on the ground, because the Growler was derived directly from the Super Hornet, a proven aircraft platform. They share the same airframe and engine and have approximately the same in-flight weight. In order to properly compare noise levels between the Prowler and the Growler, extensive noise analysis of the Prowler was completed in 2003 to ensure the Navy had updated measurements. With updated reference noise data available, an operational noise comparison between the Prowler and the Growler was conducted for NAS Whidbey Island and OLF Coupeville in May 2004. This study evaluated and compared the noise modeled from normal flight operations and ground run-ups of the two aircraft types. The comparison of sound levels clearly demonstrates that the Growler generated less flight noise than the Prowler. This noise reduction is driven by the better flight characteristics of the newer Growler. While the two aircraft sound different, the Growler has similar or lower sound levels under most conditions, And the growler also climbs away from the ground more quickly than the prowler, which also reduces noise impacts. In closing, if you would like more information about aircraft noise and how the Department of Defense models noise, I would encourage you to visit the Department of Defense Noise Working Group website.